As another example then, let's look at the football league table data. So this is the league table from the 2019-2020 disrupted COVID season, where Liverpool won the league. So for each team, I'm only showing the first 10 teams in the league here. For each team, we have the number of wins scored by the team, the number of draws, the number of losses, the goals scored by the team, the goals conceded by the team, and the goal difference. So first of all, note that there are 6 variables in this data, but there's only really 4 bits of information. If I tell you the number of wins and the number of draws, and assume as long as you know the total number of games is 38, you can work out the number of losses. Similarly, if I tell you the goals scored and the goals against, you can work out the goal difference, this column minus this column. Okay, so 6 variables, but only 4 bits of information. So we're going to expect to find 2 eigenvalues that are 0, because there's 2 directions in the data that are completely uninformative. So if we compute the sample mean vector of these data, first of all, we get the following vector. Now we can see that the average number of games won is 14.4. That, by definition, has to be the same as the average number of games lost. Yeah, the number of games won, and the sum of them must be the sum of the games lost. And similarly, the sum of the goals scored, or the average goals scored, must be the average the goals against. Okay, so these numbers must match as well. So if we work out the sample covariance matrix, we get the matrix here. And then if we do principal component analysis on this data, or if we take the Eigen decomposition of it, we find the following eigen values. So the first thing to note is that, as we said, the last 2 eigenvalues are 0. They're not exactly 0 because of a numerical error on a computer, but essentially 0. The first eigenvalue is much bigger than the others. So 1300 for the first eigenvalue compared with only 72 and then 8 for the next one. Okay. So given we've just been talking about screw plots, let's have a look at the proportion of variability explained by each of the principal components. Okay. So if we look at lambda 1 divided by the sum of the lambdas, we can see that the first principal component here explains 94% of the variability. The second principal component explains 5% of the variability, and so on. The third and fourth principal components each explain less than 1%, and so we can essentially ignore them. It's only the first 2 that we take into account, because they explain collectively about 99% of the variability. The fifth and sixth principal components here are literally useless, uninformative. They don't tell us anything at all about the data. So one thing we often do is produce a scree plot. So a scree plot is just a plot of the eigen values against their index. So here we had the first eigenvalue, divided by the sum. The first eigenvalue here was explained about 95% of the variance. That's way up here. The next one will explain about 5% of the variance, and the rest essentially 0. Okay. So often when we're doing analysis, we decide only to look at some of the principal components, leading principal components. And there's various ways of choosing how to do this. One common way is just to say, take enough components to explain 90% of the variance. So in that case, we could just take this first one. Okay. So we can work out look at the eigenvectors themselves here. Okay. So this is the first eigenvalue vector, this is the second eigenvector, and the others we've said don't represent anything meaningful in the data, so we can just ignore them. So the first principal component, the first transformed variable, is given by these loading values times by the data. Okay. So for example, y1 would be minus 0.17 times the number of wins, or the centered number of wins, so the wins minus the average number of wins, plus 0.028 times the number of draws, and so on. So one thing we often do is try and give interpretations to the principal components. So if we think about this first principal component here, we can see it's measuring largely something to do with the number of goals scored. So a negative value seems to indicate better performance than a positive value, and you have a large negative value if you scored lots and you had a big goal difference and you conceded relatively few. Okay. So if we really look at the league table in terms of the principal component scores, if we reorder them, you would find that Manchester City had the largest principal component 1 score because they had a better goal difference than Liverpool. So the second principal component score here seems to indicate how exciting the games you're in. Okay, so you have a large principal component 2 score if you're in games where there's lots of goals scored and lots of games conceded. Okay. So the teams with a large PC2 score tended to be in high scoring games. So if we plot the variables by their principal component scores, we've got PC1 on the x-axis here, so that explains 94% of the variance. PC2 on the y-axis, that explains 5%. You can see we get a spread of the teams. So Liverpool and Manchester City have the most extreme PC1 score, okay, but Manchester City were clearly in more high-scoring games, so they have a higher PC2 score. So if we produce a new league table based on the PC1 score, we can see it slightly reorders the teams. So we have Manchester City at the top now, if we rank by PC1, followed by Liverpool and so on. Okay. So what happens if, instead of doing principal component analysis on the covariance matrix, we use the sample correlation matrix? So if we repeat the analysis, using R instead of S, we get very different eigen values now. So the main thing to note is we still have 2 zeros, as we know we must, because there's only 4 bits of information, but that the eigenvalues drop off much more slowly. Okay, so the first eigenvalue is no longer so dominant. And if we look at the eigenvectors, we can see now they give a much more even weighting across all the parts of the data. So you'll have a large negative value for principal component score 1 if you won a lot, scored a lot, and conceded relatively few. Okay. So again, if we look at our league table, according to the principal component 1 score, we get a league table that looks much more like the original league table now. Okay, so doing PCA on the correlation matrix rather than the covariance matrix gives to me a much more pleasing analysis here. Okay, and I think it makes sense to use R instead of S, in that if we go back to the original table, the number of games lost is quite small, or the number of goals won is quite small compared to the number of goals scored. Okay. So the variables have different scales to begin with. So by using the correlation matrix, we rescale all the variables to make them all equally important in the analysis. And I think that gives a more pleasing form of PCA in this case. Again, so if we look at the scatter plot of the data points according to the new principal components worked out using the correlation matrix, we see a similar picture to before, but now Liverpool are inching ahead, okay, on PC1 score. Okay, and PC1 score is no longer so dominant; it only explains 75% of the data variance, and PC2 score explains 21% of the variance. Okay.